Hello and welcome back. Today I'll be talking about finding the different centers of a triangle. You can have several centers based on different conditions, but the four ones that are used the most in geometry are the orthocenter, centroid, circumcenter, and the incenter. The orthocenter is formed by altitudes, the centroid is formed by medians, the circumcenter is formed by perpendicular bisectors, and the incenter is formed by angle bisectors. Now, you might be wondering, what do any of these lines even mean? Well, let's start off with the simplest. An altitude. An altitude is a line drawn down from a vertex to the opposite side of a triangle at a 90-degree angle. This means that the line drawn from the vertex has to be perpendicular to the other side. A median is a line drawn from the vertex of a triangle to the midpoint of the opposite side. An angle bisector is simply a line that bisects an angle in the triangle. The final line, a perpendicular bisector, is a line that goes through the midpoint of a line, in which it is also perpendicular to the same line. It is basically an altitude and a median combined, however, it does not have to intersect the vertex. To actually get these triangle centers, you need to find out where these types of lines intersect. In this example, we can see that the three perpendicular bisectors intersect at this point, meaning that this would be the circumcenter. Now, onto the properties of each of these points. A circumcenter is equidistant from each vertex of the triangle, meaning that if this distance were to be 5 centimeters, then these other two lines would also measure 5 centimeters. Since it's equidistant from each of the vertex, if we were to place the point of a compass on the circumcenter and the pencil on the vertex, we could draw a circle around the triangle in which the triangle is perfectly circumscribed within the circle. A centroid has a special property. When a centroid is formed, it divides a line into a 1/3 and 2/3 ratio. As you can see here, the length of this line is 10 centimeters, and this line measures 20 centimeters, meaning that this entire median measures 30 centimeters. If you don't believe me, try constructing your own centroid and see the measurements. An orthocenter has no properties whatsoever. And now, the final center, an incenter. An incenter has the special property in which it's equidistant from each side of the triangle, but in order to find the side length, you have to draw an altitude from the incenter to the side of the triangle. After drawing these side lengths, you could place your compass on the incenter and the intersection point of the altitude and the triangle side, and you could perfectly inscribe a circle within the triangle. This means that the distance between the incenter and the sides is also the radius of the circle. This also means that the three different altitudes formed between the incenter and the triangle sides are congruent. Now, let's try some practice problems. Here's our first problem. We're given triangle ABC with the perpendicular bisectors D to G, G to E, and G to F, and we have to find these indicated measures. Well, firstly, let's recall the properties of a perpendicular bisector. Perpendicular bisectors intersect at a circumcenter, which is equidistant from each of the vertices, in which the line segments would be B to G, G to A, and G to C. All the line segments I just mentioned are congruent to each other. The next property is that a perpendicular bisector forms a 90-degree angle. And the third one is that it bisects a line segment. Using this information, let's try to answer the questions. We have to find out the length of A to G. Since it's a distance from the circumcenter to the vertex, it's going to be the same as line segment G to C, which is 25. The next segment we have to find is C to F, and since a perpendicular bisector bisects a line segment, A to F is congruent to F to C, which means that line segment F to C is 24. Next up we have C to E, and as previously discussed, a perpendicular bisector bisects a line segment, meaning that B to E is congruent to E to C, meaning that E to C is also 15. Again, B to D is simply going to be A to D, as a perpendicular bisector bisects the line segment A to B. So line segment B to D is going to measure 20. Line segment A to B is simply going to be AD plus DB, which is 20 plus 20, which equals 40. The same applies for line segment A to C. It's going to be 24 plus 24, which is 48. And for the final question, the measure of angle ADG, we know that a perpendicular bisector forms a right angle, which is a 90-degree angle. So we know that the measure of angle ADG is 90 degrees. On to the next problem. Here's our second problem. We're given that in the diagram of ABC, line segment A to E and C to F are medians. That's this segment over here and this segment over here, intersecting at this centroid. Measure of angle EAB is 39 degrees and angle FCB is 19, and angle B is 82 as marked. Calculate angle ADC. Well, firstly, what I advise to every single person doing a triangle angle problem is to calculate every single angle possible, whether it be through linear pair postulate, all angles in a triangle add up to 180 degrees, vertical angles theorem. Try add in everything you know. But for now, I'm going to list every important angle. Let's do what we can with our triangles over here. Line segment A to B is divided into two due to point F, which is actually the midpoint, as C to F is a median, and a median divides a line into two. But let's look at this. Line segment F to D is a perpendicular line. So doesn't that mean line segment F to D is a perpendicular bisector? Let's look over here. Line segment C to B has E as their midpoint because of median A to E. And line segment E to D is perpendicular. So isn't line segment ED also a perpendicular bisector? These two perpendicular bisectors meet at point D. So this means that point D is actually a circumcenter. And we know that a circumcenter is equidistant from each vertex, so we can add these markings as shown. We can also draw a third line over here from vertex B. Add the variable x over here, and we can put our next angle over here as 180 minus 129 minus x, in which we would get 51 minus x as our angle over here. We see that this triangle over here is an isosceles triangle, and these two angles are corresponding. By CPCTC, as these two triangles are congruent, we know that this angle must also be 51 minus x. Now, for our angle over here, we simply have to subtract 51 minus x from 98, and we get 47 plus x. Same concept over here. These two triangles are congruent, meaning that these two angles are corresponding, so this angle over here also has to be 47 plus x. And now we just have to add all of this up together, and we get 196. Subtract that from 360 because this is a circle, and the angles in a circle add up to 360. So simply subtract this from 360, and we get our final angle measure as 164. On to the next problem. Here's the final problem we'll be discussing. We're given that triangle ABC is an isosceles triangle with vertex A, with D as the centroid, and we have to find these following measurements. Well, let's lay out the basis. If we know D is the centroid, we know that line CF, line GB, and line AE are all medians. So when we have to find the measurement of line G to D, we know that this is 1/3 of this entire length, and D to B is only 2/3. And 1/3 is half of 2/3, so G to D would be half of 12, which is 6. Next up, we have to find F to B. These two problems are extremely simple, and we know that the property of a median is dividing a line into two. So if this is 16, this also has to be 16, as line AF would be congruent to FB. And the next problem is a bit confusing for some people. When given a triangle like this, most people will simply look at the isosceles triangle and assume that line G to B is congruent to F to C. You need to actually find a way to prove these two lines congruent. So this is how you would do it. First, we need to take line AE and prove that it is congruent to itself through reflexive property of equality. Next up, we have line CE congruent to line EB through the property of a median. And then we know that AC is congruent to AB through the definition of an isosceles triangle. So we know that triangle AEB and triangle AEC are congruent to each other through side, side, side. Now we have two congruent triangles, and we have these corresponding angles. We know that it's a linear pair. When we have two corresponding congruent supplementary angles, we know that they're going to be right angles. This means that triangle AEC and triangle AEB are both right triangles. Let's analyze our triangle once more. We know that DE is reflexive to itself, and we know that CE and EB are congruent. Using this, we can say that triangle DEB and triangle DEC are congruent to each other through leg-leg. If you don't know what leg-leg is, I recommend watching my previous video as it explains how to prove right triangles congruent. Now, we know that these two triangles are congruent, and then through CPCTC, we can say that DC is congruent to DB, so then we know that this is 12. Next up, we can use the property of a centroid to say that DF is equal to 6, and then we can say 6 plus 12 is equal to 18. Thank you for watching, and if you have any other questions, please leave them down below, and I'll be happy to answer them. Goodbye.